Okay, so I turned on the recording. So please start. It's very nice to have Kiumars Kaveh today at our seminar. Please.
Thanks for the invitation. It's great to present some results to this group of smart people and experts, and also see a lot of good friends that I haven't seen for a few years. So I'll talk about some relatively recent results about bundles on toric varieties and buildings. So a couple of years ago, I had no idea of the notion of building. I attended a talk about toric vector bundles on toric varieties in some program in a Fields Institute, and I just got familiar with this, with the concept and the Klyachko's theory. And then we started thinking about it, and then we accidentally realized that it's related to notion of buildings, which is very well studied in Lie theory, starting with the foundational work of Tits and Bruhat-Tits. So I'm no expert in the theory, and I'm still learning the theory of buildings, but I think it's an interesting connection I'll talk about in this talk about vector bundles and more generally principal bundles and toric varieties and buildings. I start with some quick review of toric varieties. I hope it wouldn't be too boring. I realized I forgot in my abstract to mention that this work is joint with Chris Mannon, who I checked and was earlier a speaker in the seminar, and Boris Sevlichovsky, who is a postdoc in University of Pittsburgh and was one of your students at HSE. I pride myself in the department that I'm one of the few people who can spell the English spelling of Boris's last name. Other people say just Boris T.
Yeah, okay. It's not that easy, right?
Even in Russian, I think it's very unusual combination of sounds.
Okay, so quick review of toric varieties. I'll work over C complex numbers, but other algebraically closed fields are just work over other algebraically closed fields. C star is C minus 0. Torus, algebraic torus is C star to the n. It has lattice of co-characters or one parameter subgroups and lattice of characters. T goes to powers of T is a one parameter subgroup. A bunch of coordinates on torus go to a monomial is a character. Laurent polynomials are a coordinate ring of torus. And toric variety is basically natural compactifications where a given Laurent polynomial has nice behavior at infinity. These are projective toric varieties, and this is motivation to study toric varieties and construct toric varieties from a point of view of Newton polyhedra theory. A general, just formal definition is that torus acts on an irreducible normal variety with finitely many orbits. We can, without losing generality, you can assume the open orbit has no stabilizer, so it's T. So basically, you have a variety who has an open subset isomorphic to T. It has an action of T. One of the orbits is isomorphic to T, and the other orbits are at the boundary of that open orbit. Okay, first example is torus acting on projective plane by just acting on the first two homogeneous coordinates. And you can associate to this picture a partition of plane R2 into cones, 3 cones, and the geometric and way of seeing this is that you look at one parameter subgroups, T to A, T to the B, and see what's the limit as we go to 0 or infinity, depending on the convention of, say, just one point in the open orbit, 1, 1, 1. And then I like to show this in my talks. So you have 6 limit points, actually 7 if I consider T to be A to be 0, B to be 0. It's just a one parameter subgroup is constant. So I have the constant one, which is 1, 1, 1. And then, so depending on where this A, B lands, these inequalities, you have different limits. So you have this picture. So if one parameter subgroup is here, you have one limit here, another limit, on this raise, another limit, so on. And this is also summarized in this triangle. So this is an example of a fan, and this is a polytope normal to the fan. I'll not talk about the polytope picture, but in the talk I'll use the fans a lot, reference the fan. This is a fan. So this is a bunch of cones, polyhedral cones, all centered at origin and overlapping on their faces. Looks like a fan. More formally, a fan is a union of bunch of cones in the vector space associated to co-character lattice, which is just a copy of Rn. We have rational polyhedral cones, which are convex rational polyhedral, which are strictly convex, means they do not contain a line. So they are pointed cones. This is a strictly convex, but this cone is not a strictly convex. It's not pointed. And then you have a finite union of this rational polyhedral strictly convex cones that, first of all, for each cone in the collection, any face it's there, and they overlap on common faces. Okay, and the standard theorem in toric geometry is that a category of fans is equivalent to category of toric varieties. For the these are, yeah, and just okay, I think that hopefully is familiar for everybody. And for each sigma in the fan, I have an associated affine toric variety. So in cones corresponds to affine toric varieties. General toric varieties correspond to fans. And I denote that by U sigma. It's an open torus invariant subvariety inside X sigma. It's affine chart T invariant. And for the rest of discussion, we fix a point in the open orbit in the torus. Open orbit is U0, corresponding to origin in the fan. It's isomorphic to the torus itself. And then I fix a point in that open orbit. Fixing a point amounts to fixing an isomorphism of torus and open orbit. Then I recall classification of torus equivariant line bundles over toric varieties. So by that we mean a line bundle over toric variety and the lift of action of torus to the line bundle such that the action is linear on the fibers, on the lines. Okay, so this is a equivariant line bundle, or for short, toric line bundle. And it's well known that T line bundles, torus equivariant line bundles L, are one-to-one correspondence with piecewise linear functions on sigma, which are integral, meaning that integral means send lattice points to lattice points. Okay. Recall that sigma lives in the vector space associated to co-character lattice, which we think of it as Zn. And so the piecewise linear mean that restriction to each cone is a linear function, It's not may not be globally linear, but restriction to each cone is linear, and sends lattice points in N to integers. And here, when you can also think that each T line bundle corresponds to a T invariant Cartier divisors. I have written here one-to-one correspondence, but to be more precise, I need one extra data beside the line bundle. I need to look at this fiber of the line bundle over my distinguished point in the open orbit and fix an isomorphism of that line with C, meaning that basically fix a non-zero vector here. So after fixing that, this becomes one-to-one correspondence. This is a simple fact, but sometimes becomes confusing, at least for me. Okay. So what is the data of a piecewise linear map with respect to the fan? It's if you have a bunch of cones representing the fan, then you look at the rays of this fan, meaning one-dimensional cones, and you look at some fixed vectors on each ray. So a piecewise linear function assigns a number to each element, each of these vectors on the rays. So it's for each ray. So for each ray, you have a number. Where did I write it? For each ray, by the way, sigma 1 is my notation for one-dimensional cones, which we call rays. In the fan, you have finite number of them. For each ray in the fan, you have a number, which is determines the linear function on this ray, which is value on some fixed vector, say a primitive vector. And then if you have a cone, these numbers should come from one linear function restricted to this cone. So we say that data of a toric line bundle, is the numbers associated to each ray, such that for each sigma, the corresponding numbers corresponding to the rays in the fan are compatible. Compatible means they come from one linear function. They are values of a linear function evaluated at rays. Okay. If the cone sigma is simplicial cone generated by linearly independent vectors, this is no condition. But if it's not simplicial, if the rays are linearly dependent, then you have these guys should satisfy the linear relations. Okay, and the construction, basically the construction of this piecewise linear function is simple. We look at the divisor. It's each invariant, torus invariant irreducible divisor or prime divisor corresponds to a ray in the toric variety. Your invariant divisor is a linear combination of them. The values of the linear function, piecewise linear function on the rays or on primitive vectors is basically the coefficient of that primitive prime divisor. Again, depending on the convention, some textbooks put it minus. And the fact that D is principal divisor, it's a Cartier divisor, it can be shown that it's principal over this affine charts. This would imply that restriction of phi to each cone is linear. That's relatively a straightforward stuff, but very beautiful. Okay. Okay, sorry. I hope this review didn't take too much time.
No, not at all. I'm sorry. Could you please go a bit back? So could you please repeat this? Phi is what?
Phi is a piecewise linear function. Piecewise linear function, which is integral, means sends lattice points to lattice points, integer points to integer.
Okay.
It's defined on the fan, which this bars means union of code in the fan or
Okay.
support of the fan. Usually for most of the time we are interested in fans which are complete, cover the whole vector space Rn. With a piecewise linear function, is that the definition is okay?
Okay, yeah, thank you.
Okay. So it's restricted to each cone, it's linear and sends lattice points to lattice points. A restriction to each cone gives us the principal divisor, which is the representing your line bundle on the affine chart corresponding to that cone. And you have locally principal divisor. Local is given by a principal divisor, which then would correspond to a linear function on the cone. And yeah, that's it. And it all comes from that the line bundle has a torus action, which translates to the divide. It's represented class by divisor class of torus invariant locally principal divisor. Okay, now we go to we increase the rank of the bundle and consider general vector bundles, not just rank 1 line bundles, and that's I'm going to explain the famous work of Kliatchko on classifying torus equivariant vector bundles. He used it, I think, from what I know, but haven't really read. He used it in his proof of Horn's conjecture, and on which he gave a ICM talk, I think in 2000 or something. He needed to classify vector bundles on a projective plane, and then he just classified vector bundles over any toric variety. Torus equivariant. But classification of toric vector bundles it goes back to Kaneyama, but his data is in terms of some co-cycles and stuff, and it's harder to use than Kliatchko. I think Kliatchko is much more natural and easier to use. Okay, example of a vectorus. Okay, just quickly recall. You have a variety, or in this case, toric variety. You have a vector bundle over it. We say toric vector bundle if the action of torus in here lifts to a linear action on upstairs. So action between fibers is linear. And this theory and classification and understanding these vector bundles is much harder than the line bundle case. Already line bundle case involves a lot of interesting convex geometry and polyhedral theory and stuff. This vector bundles is much harder. Combinatorics, in my opinion, there is a lot of interesting work done, but not some important questions, and the combinatorics not completely understood, in my opinion. Anyhow, so we fix a toric vector bundle of rank R. This is the distinguished point in the open orbit we fixed forever. The fiber over this guy is a R-dimensional vector space I refer to as E. So whenever we see this E, it for us in this talk denotes R-dimensional vector space. That's it. Okay. Then Kliatchko says that these toric vector bundles are in one-to-one correspondence, or better to say isomorphism classes of this kind are one-to-one correspondence with families of Z filtrations, and I have to say decreasing filtration. Filtrations of this vector space E. Filtration by subspaces, vector subspaces. So you have subspaces decreasing indexed by integers, Z filtration. So E0, E-1, E0, E1. For each ray in the fan, you have one of these filtrations. For line bundles, for each ray in the fan, you had a number, you had an integer. Here, for each ray in the fan, you have a filtration. Okay, so it's already more complicated data. I also want to say that if you have if you have just E is C.
Kiumars, and how can number be interpreted as some trivial filtration or?
So that's exactly what I'm writing now. So
okay.
if R is 1, number is tells you, so you start from a C and then you go to 0. You only have to say at which place you go from C to 0. You just, that index is that number A row, which you have C and then you have 0. So you have to just say at which position in the filtration, which I you go from now C to 0. Where is the jump from C to 0? That's the number A row.
So this filtration is just a set of R integer, well, of R numbers, some of which are infinity or minus infinity.
No, so sorry, you mean in the rank 1 case?
No, the rank R case. So
in the rank R case.
Okay, no, right. No, it's more complicated than that.
Yes, it's more complicated.
Yes.
You just have some. It's basically another way of thinking of a filtration is you look at the jumps at the filtration. So going where you have from whichever way you want to think, going from 0 to E, you look at where you have a jump. So you have a flag of subspaces, but then for each subspace, you have to say which position in the filtration that jump happened. So you have a flag and an integer associated to each subspace in the flag. So I call it a labeled flag. So a filtration is a labeled data of a labeled flag, a flag of subspaces and the number assigned to each subspace, which is increasing. Like this.
But the flag can contain any number of subspaces between 0 and R. So
yes,
between
yes.
1 and R.
It could be a partial flag, could be a complete flag, yes. The flag could contain any number of subspaces, but of course, less than or equal to R.
Okay,
we'll get to that in a second, in fact. Okay, so and then what is the piecewise linearity that the previous for line bundles? So for each the numbers associated to rays in the same cone, rays in the same cone, then their numbers which should come from one linear function. There are values of same linear function. So in the rank R case, in the vector bundled case, translates to this, which I'm going to explain. So, you have this data of filtrations for each ray, and they have to be compatible. So what is the meaning of compatible in the sense of Klyachko? So you pick any cone in the fan, which corresponds in fact to affine chart. It has some rays, the cone. Then compatibility means there exist these two data. Previously, incompatibility for line bundles means there exists a linear function. Here, there exists a basis for your vector space and a bunch of characters or linear functions. Okay, such that the ith space in the row filtration is spanned by these basis elements, by the basis elements that pair with the primitive vector bigger than I. Okay. So these characters and the row determine a subset of the basis, and that subset is spans this filtration. It's little bit, you have to think a little bit about it to understand it. So
sorry, could you say it again? So they exist, such V-row?
There exists a basis.
Yes.
So for each sigma, you have these two data.
Yes, what is V-row?
A V-row is, sorry, I didn't. It's the primitive vector along.
Sorry, what is primitive? Primitive means
like
integer.
yes,
vector?
a smallest integer vector. We just have to want a way of fixing one vector on row, and you take the smallest integer vector on row. Smallest or shortest is integer vector along row. So because the row is rational.
What is row?
Row is the ray. Is one-dimensional cone.
So you choose.
So for each that picture, say this is a two-dimensional fan. So you have these rays. On each one you take, each one is rational, so it means there exists an integer vector on each ray. So you pick these shortest integer vectors, and then to each one you assign these filtrations, and the filtrations corresponding to the same cone, the rays corresponding to the same cone like this, should come from a basis. So for this cone, you have a basis, and you have two basis elements. This is R basis elements and R characters, which give you these two filtrations. For this, you have another basis, another set of R characters, which give you these two filtrations. So this filtration, which is in the boundary of two cones, comes from one basis here and another basis here. Okay, I think I wrote down I didn't wrote down so for projective plane, you have these three rays. Tangent bundle of projective plane, so it's rank 2. So your E is C2. And you have a standard basis E1, E2, and then you have a filtration here. At position 1, you have this. At position rest is 0, before is C2. For this guy, you have this filtration, a line, origin C2 at position 1. And then here filtration is line minus E1 minus E2 generous. So you have 3 filtrations. With basically it means 0, 0, 0, a line, and then full space. And then you can check that these two guys come from same basis. These two guys come from same basis, and so on. These two filtrations are compatible, coming from same basis. These two compatible, and these two compatible. I haven't written down the compatibility data for this picture, but I hope this somewhat makes sense. So each space in the filtration corresponding to a ray in your cone is spanned by a subset of the basis elements. But which subset is determined by these characters and the ray. Is that okay? Should I move on?
So
yes,
you defined. Yes, yeah, sure. I think. Thank you.
Okay. In fact, after I talk about buildings, you see that this talking about filtration for purposes of Koliaschko is a great choice of data. But when I talk about building, I think it becomes more clear. It's a little bit better, easier way of thinking about it. And then this whole thing comes from this key observation, which is not difficult to prove, is that a toric vector bundle restricted to each affine chart is trivial bundle, but also the T action on that is T equivariantly trivial, meaning that it's isomorphic to a trivial vector bundle on this chart, and the action of torus on this guy comes from one homomorphism. So T equivalent trivial means that you have the T action comes from a homomorphism of T to GLR or GLE. So you have a homomorphism. Through this homomorphism, one acts on all fibers of this. So trivial means isomorphic to this cross E, sorry. Or affine chart cross E. This is trivial bundle. And the action of T on the fibers comes from one homomorphism. So this is proved by showing that there exists a collection of T weight sections for the vector bundle, global sections which are torus weight vectors, and they are everywhere independent. It's not hard to show that this exists. And then it implies that it's trivial. Your toric vector bundle on each affine chart is trivial and in fact equivariantly trivial. Okay, and that's the example. Now we change a gear. So that was Klyachko. He has beautiful, his paper is English translation. It's originally Russian. It's toral vector bundles on, yeah, I think that's toral vector bundle, something like that. It's a beautiful paper, very dense, full of important, interesting results. And he, in terms of filtration, he does lot of, describes a lot of geometric data about this. He also about vector bundles, and also he has important conditions on when a vector bundle splits into sum of line bundles. I think still this paper can be source of new discoveries. Anyhow, so now I give a quick review of buildings, but I don't know really general theory of buildings beyond the basic definitions, but I'm going to talk about the building associated to a linear algebraic group G. In most of literature, usually they take G to be semi-simple group, but in fact, building of a linear algebraic group and its semi-simple quotient are the same. Okay, so what's a building? It's an infinite, it's an abstract simplicial complex, means a set which represents vertices of a simplicial complex, and simplexes are subsets of this abstract set of vertices, which each subset represents the simplex with those vertices. And if you have a subset in your collection, you have to have all faces of simplex, or meaning all subsets of that finite subset in your collection. So it's basically abstract simplicial complex visualized by some simplices which overlap on their common faces. Okay, so it's a very general, simple definition. In our case, we want it's an infinite, so you have infinite number of simplices. Okay, but you also have in this, this is definition of an abstract simplicial complex, but a building has some distinguished finite subcomplexes. So some certain finite union of these simplexes, they call them apartments. Okay, which satisfy some abstract axioms. Tits crafted these axioms so that they actually guarantee that this building comes from a linear algebraic group. Okay, but what I'm going to explain is what, given a linear algebraic group, what is the complex associated to it. Are used in classification of algebraic groups. Tits as notion of a Tits system and so on. They are kind of discrete analog of symmetric spaces for Lie groups. For this point of view, and connections with hyperbolic geometry, blah, blah, blah. You can look at this interesting survey of Lesion G. Again, I haven't read it, maybe just few pages of this nice survey article, but in case you are interested. So we have a linear algebraic group. This is the abstract complex, which is the Tits building. So simplices are indexed or corresponds to parabolic subgroups. We call that parabolic means this over P is a projective variety or a complete variety. And if you have inclusion of two parabolic subgroups, the simplices of the inclusion is the opposite direction. Each apartment corresponds to a maximal torus. I denote maximal toruses tori by H because I'm reserving T for the toric variety, torus in the toric variety. And so how to think about it? Each apartment associated to H is Coxeter complex of this group and the torus, which means this is example of SL3. So you look at the while chambers in the co-character lattice of the torus. You have these while chambers, and then each while chamber represents one maximal simplex. And so the inclusion and overlap of these 6 while chambers is the Coxeter complex. In other words, you look at the unit sphere or unit circle in this case, and then intersect each while chamber with this unit circle, you get segments and vertices. Yeah. So these segments are one-dimensional simplices. These are zero-dimensional, and this is the Coxeter complex, triangulation of unit circle. For SL4, you have rank is 3, unit sphere is 2-dimensional, and then you have each triangle here represents one of the while chambers. And then you have this triangulation of unit sphere. These triangles and their edges and the vertices are the Coxeter complex of SL4. Is that picture understandable? So to each maximal torus, you can correspond this while chambers intersected with unit sphere, you get a triangulation, and that's the Coxeter complex, or the apartment associated to that maximal torus. So for each maximal torus, you have a different triangulation of a sphere, same triangulation of a sphere, but living in different place, different vectors. Is that okay? Everybody's quiet, so it's either obvious or something is explained very bad.
So the simplices of maximal dimension correspond to barrels.
Yes.
Mm-hmm.
Maximal simplices.
And the vertices, these numbers 7 and 20, what are they? I mean, they are the
number of
maximal parabolic.
Vertices mean the number of maximal
parabolic. What are those numbers?
Yes. Maximal parabolic.
I can't remember what is the number of. What are those numbers?
It's easy to compute, and it's okay. I'll see. We'll see that in a second. In fact, the building of SLN or GLN. Okay, and then also hopefully you may remember from this theory of Lie groups, algebraic groups, that each face. So if I fix a while chamber and call it positive while chamber, then the parabolic subgroups or the subgroups that contain that, right? So it corresponds to a choice of Borel. Sorry, B and building, I hope I'm not confused. Okay. So we fix a Borel. For GL and SLN, it means that you have fixed an ordered basis for your vector space. And faces of this guy, so we have 4 faces, corresponds to subgroups which contain that specific Borel. The whole thing corresponds to the Borel itself. This corresponds to 2 minimal parabolic, maximal parabolics, and then this corresponds to the G itself, the whole group itself. Okay, so anyhow, faces of the wide chambers corresponds to subgroups or parabolic subgroups containing the maximal torus. Okay. So now you can glue. So I'm going to construct a building, or in fact, geometric realization of this abstract simplicial complex as follows. For each maximal torus, I look at a sphere inside co-character lattice or vector space associated to this. I triangulate it using Weil chambers and take infinite union of these spheres for each maximal torus, for all maximal tori. Then I glue, so it's the infinite union, I think it's clear, I hope. Infinite union of spheres for each for all maximal tori. Then if a parabolic subgroup may contain several maximal tori, then I glue the corresponding faces in different maximal tori, so on different spheres. So in this picture, this represents a parabolic subgroup which contains your given maximal torus and Borel. But it can be, that same parabolic subgroup may be represented by another face in another maximal torus. If that happens, I glue those 2 faces. So you have a lot of spheres which are glued along their simplexes, which corresponds to the same parabolic subgroup. Okay, looks like I have to explain the example of GL and SLN. And then it should be clear. It's in case of GL and SLN, it's really linear algebra and relative position of bases in a vector space. Okay, and then just one extra definition. I have this union of spheres, which is the geometric realization of building, Tits building. I can do the same as gluing and stuff, but instead of spheres, I just take the whole vector space instead of taking the vector. So I call it, people are not interested in this, so that's basically the definition we made in our paper. We call it cone over Tits building. This infinite union of these vector spaces associated to co-character lattices of tori, and they glue them along common Weil chambers. So if a Weil chamber represents, 2 Weil chambers represent same parabolic, we glue them. Okay, now of the GLR, which now GLE. So parabolic subgroup or simplexes corresponds to flag of subspaces Okay, so each flag gives you each flag gives you a simplex, and corresponding parabolic subgroup is a stabilizer of the flag. In other words, in some basis, a block of a triangular matrix. And a vertices, which is minimal simplex, corresponds to, in fact, just subspaces, or a flag with one subspace in the middle. Maximal simplices corresponds to complete flags. And apartments corresponds to choice of a basis. Up to a scale. Sometimes a basis up to a scaling, so you are allowed to scale, multiply with a non-zero scalar each basis element. Sometimes it's called frame.
I'm sorry, you are saying that vertices correspond to arbitrary subspaces, right?
Yes, yes.
So each vertex.
I think I have to take non-trivial subspaces, I think. Not zero. I think I have to exclude 0 and C to the R.
So in other words, you're saying that vertices are parameterized by the union of Grassmannians. Is that right?
Yes, 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 exactly.
I see.
Vertices are union of Grassmannians. Yes. Apartments are bases, and then simplex. So you have an apartment associated to a basis. So you have a basis, B1 to BR, and then you have a flag. So this simplex belongs to the apartment, because this represents an apartment, this represents a simplex. And this simplex belongs to the apartment if each Fi, each element in this flag, is spanned by a subset of the basis. And the combinatorics question how many flags given a basis. So we call them, we say that the flag is adapted to the basis. So it means that every subspace in the flag is spanned by this basis elements. So to complete flags, n factorial complete flag, r factorial. So out of a basis to get a complete flag, you have to consider a permutation of these elements, like a B1, then inside B1, B2, then inside B1, B2, B3, and so on. And each permutation gives you a complete flag. And then you can compute how many partial flags you have, etc. Okay. Makes sense. And there are finite number of partial flags, and that flags in general that are adapted to a basis. And that gives you exactly this picture. So each of these corresponds to an ordering of the standard basis or some basis. And these are some partial flags as such. Okay. But a flag, as everybody knows from linear algebra, can be adapted to even a complete flag can be adapted to a different basis as well. If you make an upper triangular change of basis, it's still adapted to that new basis. So a basis, a flag can land in different apartments, infinitely many different apartments. So that's the linear algebra behind the building of GLN or SLN. Okay, maybe I have to Let's continue. So
Kiumars, I'm sorry, may I ask one
Yeah.
more question? So
Please.
if we get back to the question of Igor about this number 20 for SL4, how are we getting it here?
you have to consider all flags
Yes.
which are adapted to a standard basis. That's number.
Okay.
That's number 2. So
Okay.
number of complete flags is 4 factorial, I think.
Absolutely. Yes.
Yes.
But
Oh, no, sorry, 3 factorial.
so we have SL4, yes.
So,
So,
so when you go to yeah, so yeah, sorry,
so I'm a bit confused. So we have the vertices, as you said. Yes, you need compatible flags. Yes.
Yes, we just have to compute all flags compatible to a standard basis, and you should get all the. Sorry, 20 was number of what?
No, it's 24. It's, I think, right?
Number of
So
the triangles.
The number of triangles is 20, but the number of vertices should be 24, right?
No.
So-
Triangles are barrel,
Correct.
and barrel are 4 factorial
24.
barrels.
Yes,
No.
4 factorial is number of triangles.
So
So it's
24
this
and
is yes.
okay.
It's a dual to the permutahedron. So each triangle represent a represent a permutation. So it's 4 factorial is 24, which is number of triangles.
But then the vertices should be not 20, but I guess
Number of the vertices should be
12.
number of subspaces of any dimension. So it's number of subsets, non-trivial subsets.
so I would say it should be 15, maybe. No, I think
Yeah.
so. 4 plus 6 plus 4 plus 1.
Yeah.
So it's the number of rays in the veil fan, right?
Yes. So maybe 14.
So the number of
2 to
rays
the
in
4,
the
2 to the 4 minus 1, I would say.
-2.
-2. I think the whole space also doesn't count, if I'm not mistaken.
Okay.
Okay, yeah.
Yeah, thank you.
So 12, 14, right? Okay.
So, thanks for all the questions. And okay, during this thinking and understanding Tits buildings, and it was, as I want to say that it was, we just had to kind of understand for the purposes of toric vector bundles and toric principal bundles. I was mostly laziness of reading the standard literature, so I had to come up with my own understanding together with Chris. So we understood Tits buildings in terms of 1 parameter subgroups of G, and I couldn't find it in literature until recently that I realized that Mumford in his geometric invariant theory book has exactly the same description of Tits building. He calls it flag complex, but I couldn't find it in a standard literature. And anyhow, on buildings. So you look at 1 parameter subgroups of the group G, which just means algebraic homomorphism from C star to G. And if you think about it, in terms of GLR, so each homomorphism from C star to GLR is diagonalizable in some basis. So it's a co-character or 1 parameter subgroup of some torus inside GLR. So it's diagonal, but it could be diagonalizable in different bases. So in some sense, it lands in different apartments. So I thought so the Tits building can be realized as basically collection of all 1 parameter subgroups. But then, as stupid as I am, I forgot about some equivalence equivalence relation that one has to consider, and just recently realized my mistake and corrected it. And this correction will be posted on archive soon. And everybody who looked at the paper looks like did not recognize this mistake, but it's corrected and will be corrected on archive very soon on the paper. Okay. So you say two parameter subgroups are equivalent if the quotient as t goes to 0 has a limit in G. There is no other place for the limit to exist. Okay. In terms of one parameter subgroups of GLR or GLE, it means that if you have a one parameter subgroup, you have a linear action of C star on your vector space E, C to the R. It has some weights, which are integers. You can order them increasingly or decreasingly, and it has some weight spaces. You can order the weight spaces based on the ordering of weights, decreasing or increasing, and then add up the corresponding weight spaces, you get a flag. In other words, ith element in the flag is a span of all weight vectors of weight less than or equal to CR, one of the weights, or ith weight. Okay, you can have two different one parameter subgroups with the same weights and same flag. A weight and weight spaces determine the one parameter subgroup, but flag and weights do not determine it. That is exactly this equivalent. So they are equivalent if they have same weights and same flags. Okay, and the stabilizer of flag is the parabolic subgroup associated to the one parameter subgroup. So if you consider the association of sending a one parameter subgroup to corresponding a stabilizer of flag, it gives you a realization of Tits building or cone over Tits building in terms of one parameter subgroup. So proposition which appears in the new version of our paper and in some form is in the geometric invariant theory book of Mumford, section 2, is all parameter subgroups quotient by this natural relation. The quotient has limit at 0 or infinity. Are the lattice points in this cone over Tits building. And Tits building again was, or cone over Tits building, you have co-character lattices of all maximal tori and identify them over Weyl chambers which corresponds to same parabolics. Okay, finally back to Toric varieties. I have to also leave some room for questions or more discussions. So now that's the main theorem we have. G reductive algebraic group over C. I'm pretty sure over C may be reductive. Reductive may not be necessary, may work for every algebraic group. X sigma some to T toric variety. X sigma and T unrelated to G. Okay. Then a toric principal G bundle is a principal bundle over X sigma, principal G bundle. By definition, it has a G action, where G acts trivially on the base, no action on the base, and acts transitively on each fiber. So each fiber is a copy of G. So definition of principal G bundle. Toric principal G bundle means the action of T leads to action of P such that this action commutes with the G action. We write T on the left and G on the right at the actions. So the only requirement is that the T action commutes with the G action.
So Kiumars, sorry. So once again, you are saying that T has nothing to do with G. Am I right?
Yes, yes. T has nothing to do with G.
Okay.
The same way for vector bundle, GLR had nothing to do with the torus. Rank and the torus of the toric variety are different. Okay. And then recall that the Tits building or the tilde was cone over the Tits building, was union of infinite union of vector spaces corresponding to maximal tori, co-character lattices of maximal tori.
Kiumars, I'm sorry, may I ask one more clarifying question?
Please.
So do I understand correctly that this condition of commuting of the T commutes with G means that you can take any point from a fiber in P, and then if you know where does this point is mapped by a T, then you know where the whole fiber is mapped. Is that right?
Yes. So
Okay.
If you have fiber of X and fiber of TX, then this is a copy of G. This is a copy of G. We have a torus action from this to this, which makes gives an identification of this G space and this G space. So the it's isomorphism action of T.
Thank you.
Is a G isomorphism of these two spaces. Commute is G equivariant isomorphism.
I see. I see.
And then main I have to mention key result, important result. This was a P, the toric vector bundle over a affine toric variety U sigma is T equivariantly trivial. So you have, which means that it's isomorphic to base, affine base cross G, where T action on G is through a homomorphism from T to G. So there exists a homomorphism such that it acts, gives an action of T on G, say from left, and then it acts on the trivial bundle, and then you have an isomorphism between this toric principal bundle over affine toric variety with this. Okay, so we use in our classification, we use this result in. This was they give a classification of toric principal bundles using this local triviality and using Kaneyama's co-cycles, that kind of approach. So they do have a classification, but it's in terms of co-cycles and some other data. Our classification, which I'm going to explain just now, is in terms of piecewise linear maps and in the spirit of Koliachko. Okay. So we can define the notion of piecewise linear map from a fan instead of to R or Z. We replace it with the building, but not the building itself, but the cone over the building, which is infinite union of vector spaces overlapping on some cones. Okay, glued together along some cones. Okay, this is independent of T, this is independent of G. This is about toric variety, this is about G. Okay, so this is a finite simplicial complex or conical complex. This is an infinite conical complex. Okay, the definition is exactly what you expect. For each cone in here, there exists a vector space, or which means a maximal torus in G. So there exists a vector space in that conical complex such that the restriction of your map to sigma maps sigma to this vector space. So each cone should go to one of the vector spaces. It cannot break into several vector spaces. Secondly, it's integral. And then the map from this cone to this vector space should be a linear map, just in the usual sense of linear algebra. And it should be integral. Send lattice points here to lattice points here. Both have notion of lattice point. This is the very natural definition of a map, linear map to a building. But again, you have a building apartments are spheres. I have to extend it to vector space, and that's why you have to consider the cone over the building. Okay, and then the theorem is that isomorphism classes of toric principal G bundles are exactly piecewise linear maps to buildings. And it extends to equivalence of categories. And for example, one application is classification of symplectic or orthogonal bundles immediately, because one knows what is this building. Similar to GLN, it's given in terms of, instead of flags, you have isotropic flags. And then so in terms of isotropic flags, we can immediately get a classification of symplectic or orthogonal bundles. And maybe I say a couple of words. There isn't just, sorry, I'm rushing towards the end. There is a whole theory of Bruhat-Tits buildings, or what Mumford calls relative theory of buildings, also called affine buildings. The other example of buildings is called spherical buildings, because each apartment is a sphere or triangulation of a sphere. Here, each apartment is an affine space or triangulation of affine space. So the setting is for this, instead of a reductive group over a field, you have a reductive group over a discretely valued field, such as Laurent series, formal Laurent series or p-adic field, and so on. So you can associate to this, to a reductive algebraic group defined over the valuation ring of this valued field, a Bruhat-Tits building. The general definition, I do not have a good understanding, but basically you have the co-character lattice for a maximal torus, and you can act by reflections coming from while group, but you can also do translations coming from multiplication with uniformizer. And then you have a action of what they call affine while group, which is a permutation or reflection group, semi-direct product with translations. And then the pictures are, instead of the usual picture of 6 cones, you have that, but also translations. So you have a triangulation of affine space, like 2-dimensional affine space. For SL2, you have this picture, and so on. And then you can, affine building becomes the infinite union of Euclidean spaces or affine spaces. This picture does not have, because of the translation, does not have origin, distinguished origin, as origin is shifted. So you have notion of affine space with a triangulation associated to its maximal torus, and they are glued according to parabolic subgroups along these segments or triangles. And then there is a exact description of it in terms of, for GLR or SLR, in terms of lattices in the vector space K to the R. I think I skipping that side. So for GLR or GLE, all full O modules, full rank O modules in your vector space are vertices of the building, and they correspond to affine Grassmannian. Previously, union of usual Grassmannians were vertices of the building. Now the affine Grassmannian parameterizes vertices. A certain chain of these O modules gives you the other simplices, and etc. Sorry for rushing, but just our new result is with Boris and Chris. Somehow they rhyme, Boris and Chris. And not yet published on arXiv, that toric vector bundles and toric varieties or toric schemes over a discrete valuation ring O are given by piecewise affine maps from the polyhedral complex of the toric scheme to this piecewise affine, to this affine building.
I'm sorry, could you please repeat what is this X pi?
Yes, that's sorry. I was trying to cheat and not explain it. So if you have a toric varieties are classified by fans, but if you have a toric scheme, instead of defined over a field, if you want it to be over a discrete valuation ring, it's classified by polyhedral complexes in NR. And more precisely, it's NR cross 1. So NR put at level 1. No, polyhedral complex means you have some rational polytopes, polyhedrons instead of cones. You have rational polyhedrons. And these are what they classify as toric schemes over a discrete valuation. The construction of, if you have such a thing, constructing the corresponding toric scheme is not difficult. It's basically, you have a usual toric variety, a toric scheme over DVR is a usual toric variety, which you can degenerate in a one parameter family to 0. And it may degenerate into union of toric varieties. Okay, so it's toric. It's a data of a toric variety together with the one parameter degeneration of it. That's how you can think about a toric scheme. Or a toric, yeah, that's, and it's important, this notion of varieties over discrete valuation rings are of interest for arithmetic geometry people working on models of varieties over local fields and so on, like varieties over p-adic field or p-adic integer. Okay. So to construct, so you have a polyhedral complex like this in one dimension. You have just a bunch of segments overlapping on endpoints. And then you can add one extra dimension, R plus, and then construct a fan lying in the positive part. You can construct a fan by considering cone over this polyhedral complex. So you get this. Construct the usual toric variety of this fan. I call X sigma tilde. Sigma tilde is the fan over that polyhedral complex. So it's an n plus 1 dimensional toric variety. If you fiber product it with a spec of your discrete valuation rings, you get that toric scheme. It's sorry, I think because I have to go in a few minutes, I think I leave that.
Very briefly here, you said there's a, what degenerates into what in this picture? Which toric variety degenerates into the union?
Toric variety is, you have your, the toric variety is, you have a fan here.
Uh-huh.
And this, you have, gives you a fan. This is the fan in level 1. Sorry, this is a polyhedral complex, which is the fan at level 1. And then you have fan at level 0, which is basically.
Oh, okay, I got it. And it generates into the.
Which is the asymptotic. So you have these two rays, these two infinite polyhedron. They are represented by these two rays downstairs. So this is asymptotic of this polyhedral complex, or sometimes they call recession fan or recession cones. So asymptotic of this complex is downstairs is a fan. So this fan represents the generic fiber. So you have 0 and 2 multiplied. the generic fibers are your family, and then the special fiber at 0, it's like you have a variety over Laurent series, but it says you can let t equal to 0. And then after you, when you go to t equal to 0, your variety becomes, when t is not equal to 0, your variety is a toric variety. When t goes to 0, it decomposes into union of toric variety.
Yeah. Which fans are they given by?
The fan can be understood from the normal fan of this polyhedra.
Okay, so they correspond to the parts in this.
So you look at the vertices in that. Sorry, not normal fan. Sorry, not normal fan. Let me correct myself. You can look at the vertices here.
The
You
face
look at
fans.
locally the fan with that origin. Suppose this is origin, it's a fan. So it's this is a projective line.
Yeah, I think I understand.
So you have a projective line which are overlapping on something.
Yeah, okay, thanks. I think I got it.
So you have a projective line which degenerates to some projective lines collude together. So, sorry if I was rushed at the end. And by the way, this description of toric scheme goes back, is explained in the original book of toric and what is it? Toroidal embeddings of Mumford, Kempf et al. This is one of the classical references from 70s about toric varieties. It's very old, but as far as we know, there is no description of toric vector bundles on this, which we present.
Okay, thank you very much.
Yeah, I think I have to go to the meeting.
Yeah. As far as I remember, you told us that you have to be there 7 minutes ago. Yeah.
It was delayed 5 minutes, so it's starting now.
Okay, then thanks a lot for your extremely interesting talk. So actually, it was very, very inspiring. Thanks a lot.
Thank you.
Thanks, Kiumars.
Thank you. It was great to see everybody, and thanks for all the questions.
It was nice seeing you. Yeah.
Nice seeing you. Goodbye.
Bye-bye.